The primary advantage of the software managed approach is flexibility. The OS can use any data structure it wants to implement the page table without necessitating hardware change. Another advantage is simplicity, as seen in TLB control flow. Line 11 in figure 19.3, in contrast to line 11.9 in figure 9.1. The hardware doesn't do much on a mist. Just raise an exception and let the OS TLB miss handler do the rest. So this software-based handling of TLB is more flexible compared to hardware because it's just in the OS. We're only dealing with software, unlike the hardware. It also has less code compared to the hardware counterpart as seen in the previous video, but I'm gonna copy and paste this as well for your reference. So here's the software. As you can see, it only has 11 lines of code. So once it raised the exception on TLB miss, it just goes back, or it's just activate the page table because it's a TLB miss. So here you need to do the linear page table data structure, which has a base register, etc., before you get into the software part or OS part, and then retry the instruction if it misses it. Aside TLB valid bit or equal page table valid bit. A common mistake is to confuse the valid bits found in a TLB with those found in a page table. In a page table, when a page table entry PTE is marked invalid, it means that the page has not been allocated by the process and should not be accessed by a correctly working program. The usual response when an invalid page is accessed is to drop to the OS, which will respond by killing the process. So, a valid bits found in TLB in the software code is different from a valid bits found in page table, because in a page table, when a page table entry PTE is marked invalid, it means that the page has not been allocated by the process, meaning that physical frame is not allocated by a process and can be allocated to other process and should not be accessed by a correctly working program. While in TLB, a valid bit means that we already have that, we don't need to access the page table for further requests. A TLB valid bit, in contrast, simply refers to whether a TLB entry has a valid translation within it. When a system boots, for example, a common initial state for each TLB entry is to be set to invalid because no address translations are yet cached there. So after the first boot up, of course, the TLB usual response is invalid bit because there's no recently accessed or temporal locality has been done to access some data in the system by the process. Once virtual memory is enabled and once programs start running and accessing their virtual address spaces, the TLB is slowly populated, and thus valid entries soon fill the TLB. A TLB valid bit is quite useful when performing a context switch too, as we'll discuss further below. By setting all TLB entries to invalid, the system can ensure that the about to be run process does not accidentally use a virtual to physical translation from a previous process. So this invalid bits from TLB is also useful to avoid overwriting from the same processes or from different processes during context switch. So TLBs, what's in there? Let's look at the contents of the hardware TLB in more detail. A TLB might have 32, 64, or 128 entries and be what is called fully associative. Basically, this just means that any given translation can be anywhere in the TLB. So an associative meaning that any translation can be anywhere on the TLB. So that process translation can be anywhere on that same TLB. And then the hardware will search the entire TLB in parallel to find the desired translation. So the hardware will actually search the TLB to find if the translation is already there. Let's say in this example, our first TLB algorithm that did not use a software base. A TLB entry might look like this. So again, this could be a 32, 64, or 128 address space. So it has VPN, PFN, and other bits. The reason why it's as VPN and PFN is because of the translation already made once it accessed the page table at first after boot time, and other bits to know how to use the valid bits in TLB entry to determine if the process is allowed to access that. Some process are actually allowed to access that because that's actually how we communicate the code for read and execute. So some process can access the code, while for heap and stack can only be written and read too. Note that both are the VPN. Note that both the VPN and PFN are present in each entry, as translation could end up in any of these locations. So this VPN and PFN is actually a valid entry of TLB entries, because whether you use VPN and PFN, it can be used to translate to a physical frame to be able to access it quickly, and other bits as well, whether it's valid or not, or protected or not. In hardware terms, the TLB is known as fully associative cache. So for hardware terms, if those bits are in this one of bits, in terms of hardware, we call it fully associative cache. The hardware searches the entries in parallel to see if there is a match. So the hardware will look this TLB entry, like in 19.1, to see if there is a match. More interesting are the other bits. For example, the TLB commonly has a valid bit, which says whether the entry has a valid translation or not. So the valid bit will provide if it has that translation already in TLB, or if that translation is valid or not, protected or not, etc. Also common are protection bits, which determine how page can be accessed, as in the page table. So it's in the page table earlier, we have this protected bits and other types of bits. This is also included in TLB. So kind of like this hardware mechanism or features already activated in this x86 architecture, which is now translated into a more software counterpart, which is the usage of TLB cache. For example, code pages might be marked read and execute, whereas the heap pages might be marked read and write. So that's the protection bits, the same as in segmentation as well. But now we're using TLB to like mimic or project that hardware available features. There may also be few other fields, including an address, space, and identifier, a dirty bit, and so forth. So those are the available hardware features. TLB issue a context switch. So those hardware features will also be the features we will gonna use or we will gonna utilize to do the context switch or to be able to do this context switch efficiently. With TLBs, new issues arise when switching between processes and hence address spaces. So when switching with that addresses using the cache of this hardware, there's new issues arise because it's hardware helping the virtual memory to context switch. Specifically, the TLB contains virtual to physical translation that are only valid for the currently running process. So that physical translation in this TLB entry are only valid for that process, not for the other process. As a result, when switching from one process to another, the hardware or OS or both must be careful to ensure that the about to be run process does not accidentally use translations from some previously run process. So in this case, because of this hardware cache utilized by a software TLB program, they both need to work hard again to make sure that the about to be run process or the processes do not overwrite each other. To understand this situation, let's look at an example. When one process P1 is running, it assumes the TLB might be caching translations that are valid for it that come from P1's page table. So when a PF1 is running or P1 is running in that using that TLB, it assumes that the caching translations, the hardware done or the code or the software or OS code done are valid for only that process, that it doesn't overwrite other processes, that it comes from the right page table, so that the it is allocated on the right physical memory by the hardware cache and the OS. As for this example, that the 10th virtual page of P1 is mapped to physical frame 100. In this example, assume another process P2 exists, and the OS soon might decide to perform a context switch and run it. Assume here that the 10th virtual page of P2 is mapped to physical frame 170. If entries for both processes were in the TLB, the contents of the TLB would be this: 10 100 1 RWX, 10 171 RWX. So they have the same virtual private number or virtual process number. In the TLB above, we clearly have problem. VPN 10 translates to either PFN 100 P1 or PFN 170 P2. But the hardware can distinguish which entry is meant for which process. So the translation is not being done correctly because the hardware doesn't know if 10 is for that physical frame or it is for if the 10 is for 100 and if 10 is for 170. Thus, we need to do some work in order for the TLB to correctly and efficiently support virtualization across multiple processes. So to support this efficient translation so that we don't have this confusion from the hardware, like we did from our code earlier, we need some optimization to correctly and support this. So how do we support this? We're gonna make use or utilize the features of the hardware to be be able to distinguish these processes. So the crux, how to manage TLB contents on a context switch. When context switching between processes, the translations in the TLB for the last process are not meaningful to the about to be run process. So what should the hardware or OS do in order to solve this problem? Again, we're gonna go back to the hardware and OS cooperation here. There are a number of possible solutions to this problem. So we can create, of course, a better algorithm or better OS that will allow us to make use of those hardware features already available for us. One approach is to simply flash the TLB on context switches, thus emptying it before running the next process. On a software-based system, this can be accomplished with an explicit and privileged hardware instruction. So one solution is to actually flash the TLB of that process on a context switch so that it doesn't remember this translation, emptying it before running the next process. So on a software-based system, this can be accomplished with an explicit privileged hardware instruction. So if we use a software-based if-else for this algorithm instead of hardware, we can accomplish this with an explicit and privileged hardware trap2 instruction. So with the hardware managed TLB, the flash could be enacted when the page table based register is changed. Note the OS must change the PTBR on a context switch anyhow. So for a hardware based, like the hardware code we have, we need to, or the flash should be enacted when the page table based register is changed. So the PTBR, the register we have in the hardware code, will be need to adapt as well. So it's kind of like still using the previous base and bound register of the segmentation, but now we're just worrying about that PTBR values that needs to be flashed in the hardware code or hardware implementation of this TLB. In either case, the flash operation simply sets all valid bits to 0. So in either case, whether you're using the code PTBR, you just make it 0, the base register there, to return to the loop. Or if you're using a software-based, we'll just make the valid bits to 0 to make it invalid. So whether you're using a software to manage that, we'll just make it false, equal true, something in that code, the one we discussed in the previous video. By flashing the TLB on each context switch, we now have a working solution, as process will never accidentally encounter the wrong translations in the TLB. However, there is a cost. Each time process runs, it must incur TLB misses as it touches its data and code pages. So whether we did this, it still will have this TLB misses, but it's less so because we implement that flashing, or we implement the TLB already. If the OS switches between processes frequently, this cost may be high. So again, if the OS switches between processes frequently, this cost may be high for TLB misses. So if this operating system code flash it like this, it will incur a lot of misses, so the cost may be high. If we take our example, TLB from above acids, it is clear processes can readily share the TLB. Only the ACID field is needed to differentiate otherwise identical translations. Again, if we take our example, TLB from above and add ACID, it is clear processes can readily share the TLB. So if we use an ACID or activate that in the hardware, so add it in our code, it is clear that we can share the TLB for one processes, or avoid this TLB misses or cost of switching. So to reduce this overhead, some systems add hardware to support to enable sharing of the TLB across context switches. So some systems and hardware support, or some OS with some hardware support or already activated features, coordinate to solve this context switch problem or cost. In particular, some hardware systems provide an address-based identifier field in the TLB. So the OS will just write or activate that code in the hardware, which already have as an ACID field in the TLB. You can think of the ACID as a process identifier PID, but usually it has fewer bits, like 8 bits for the ACID versus 32 bits for a PID. So it's you can think of this a process identifier, but it has fewer bits, only 8 bits. So we only provide 8 bits in the hardware for this ACID, while 32 bits for an actual process identifier in the real world. If we take our example TLB from above and add ACID, it is clear processes can readily share the TLB. Only the ACID field is needed to differentiate otherwise identical translations. Here is a depiction of a TLB which added ACID field. So as you can see, we can have the same VPN of 10 and PFN different 100 and 170, but with a different ACID, and then with the same protection, read, write, and X, RWX, and the same valid bits. Thus, with address-space identifiers, the TLB can hold translations from different processes at the same time without any confusion. Of course, the hardware also needs to know which processes is currently running in order to perform translation, and thus the OS must, on a context switch, set some privilege register to the ACID of the current process. So these ACID features of hardware could be used for context switch and for sharing of data for different process, but the hardware need to know that. So to do that, the OS must, on a context switch, set some privilege register. So again, it used the register that we used in the hardware code earlier to the ACID of the current process. So it will set some privilege register to the ACID properties of that in the code, in that if-else statement. So just used an if-else equal true, if-else equal false. So as an aside, you may also have thought of another case where two entries of the TLB are remarkably similar. In this example, there are two entries for different processes with two different VPNs that point to the same physical page. So in this case, we have same PFN but different VPN. In TLB. So in this example, there are two entries for different processes with two different VPNs that point to the same physical page. This situation may arise, for example, when two processes share a page, a code page, for example, that they can read and execute. In the example above, process 1 is sharing physical page 101 with process 2. P1 maps this page into the 10th page of its address space in this same TLB, whereas P2 maps it to the 50th page of its address page. Sharing code pages in binaries or shared libraries is useful as it reduces the number of physical pages in use, thus reducing the memory overheads. So it's in the since it's as protected bits only read they use the same memory, but two different process virtualize it or are able to access it. So this is actually how you virtualize memory. This is how you give an illusion that use the same line of code in the display, but only accessing the same physical frame in the memory. Issue replacement policy. As with any cache, and thus also with TLB, one more issue that we must consider is cache replacement. Specifically, when we are installing a new entry in the TLB, we have to replace an old one. And thus the question, which one to replace? So how do we create an algorithm that will allow us to delete the cache for that process and then automatically provide it to another as our processes run? So how to design TLB replacement policy? Which TLB entry should be replaced when we add a new TLB entry? The goal, of course, being to minimize the miss rate or increase hit rate and thus improve performance. So how can we access the same code or the same physical frame with the different processes, or how can we maximize the hit rate in this TLB? So we will, of course, create some algorithm or policy. We will study such algorithm in some detail when we tackle the problem of swapping pages to disk. Here, we'll just highlight a few typical policies. One common approach is to evict the least recently used, or LRU entry. LRU tries to take advantage of locality in the memory reference stream. So a least recently used, or LRU entry. So this policy tries to take advantage of locality in the memory reference stream, assuming it is likely that entry that has not recently been used is a good candidate for eviction. So this is how we determine how the processes maximize the use of this TLB entry. If it's not accessed, therefore it is likely never gonna be accessed because of we are creature of habits, just like in about face in the previous video concept. So another typical approach is to use a random policy which evicts a TLB mapping at random. Such a policy is useful due to its simplicity and ability to avoid corner case behaviors. For example, a reasonable policy such as LRU behaves quite unreasonably when a program loops over n plus 1 pages with a TLB of size n. In this case, LRU misses upon every access, where random does much better. So another policy or algorithm is a random one, where you delete this cache table entry for that hardware translation, for that small hardware cache at random. So this has ability to avoid that corner case behavior. For example, LRU behaves quite unreasonably when a program loops over n plus 1 pages with a TLB. So when a program loop, it will behave unexpectedly for an LRU algorithm. So a random algorithm is better. Finally, a TLB entry. Finally, let's briefly look at real TLB. This example is from MIPS R4000, a modern system that uses software managed TLBs. A slightly simplified MIPS TLB entry can be seen in figure 19.4. So it uses a software managed TLBs instead of a hardware one. The MIPS R4000 supports a 32-bit address space with 4 kilobytes pages. So this is how it looks like in the real world on how this TLB are being applied. So an example is this MIPS TLB entry. It's a modern software managed TLBs instead of hardware because again software is more flexible. The MIPS R4000 supports a 32 bits address space with 4 kilobytes pages. So like what I've said, most of this system that support 4 kilobytes pages size or bit size of the virtual address space of the process supports a 32 bits address space. Thus, we could expect a 20-bit VPN and a 12-bit offset in our typical virtual address. However, as you can see in the TLB, there are only 19 bits for the VPN. As it turns out, user addresses will only come from half the address space. The rest reserved for the kernel. So this TLB, half of it is only 19 bits is reserved for the VPN or the actual byte size of the process, and the rest are reserved for the kernel. Which means those reserved for the kernel are the one activating the features, whether it's a valid or protection bits, etc. And hence only 19 bits of VPN are needed. So this VPN only half of the user address will only come from half of this address space, this 32 bits address space. So as you can see, the VPN here takes over 19 bits. The VPN translate up to a 24-bit physical frame number PFM. So as you can see, we have 24-bit here, and hence can support systems with up to 64 gig of physical main memory, 2 raised to 24 4 kilobytes pages. So these are the VPN 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32. So in this TLB entry, as you can see, are the corresponding physical frame where the VPN convert into a physical frame. So there is unused index or frame or pages rather. There are a few other interesting bits in the MIPS TLB. We see a global bit G, which is used for pages that are globally shared among processes. So these G are a global bit which is used for pages that are globally shared among processes. So this, since you have this entry and then some processes are here, occupies here, some here, some here. So this G bit are for the process that could be shared among all other processes, that could be translated into a physical frame. Thus, if the global bit is set, the ACID is ignored. So if this OS have a if else statement that if that global bit is set, the ACID will be ignored. So these are the ACID 8-bit. We also see the 8-bit ACID, which the OS can be used to distinguish between the address spaces as described above. So these are 8 bits are used to describe these processes and how their protection and validity affect on translating into this PFN. One question for you: what should the OS do if there are more than 256 2 raised to 8 processes running at a time? Finally, we see 3 coherence C bits. So here we have 3 bits for coherence, which determine how a page is cached by the hardware. So again, these are the hardware part. So these C bits or 3 bits are determine how the page are cached by the hardware. So a bit beyond the scope of these notes, a dirty bits, which is marked when the page has been written to. So this bit on the hardware side will be marked when the page has been written to. So it tracks that if that page in the physical frame has been written to by this virtual process. We'll see the use of this later. A valid bit which tells the hardware. So this V bit, if there's a valid translation present in the entry. So just this one bit, seemingly one bit, are actually used to track which VPN are related to PFN and how they are already valid or how they are marked as written to. So this is how we actually cache this in details, in real world. There's also a page mask field not shown, which supports multiple pages size. We'll see later why having larger pages might be useful. Finally, some of the 64 bits are unused, shaded gray in the diagram. So as you can see, some of this in the 32 bits for both VPN and PFN or virtual address and or for address space and physical frame are unused, which is colored gray. MIPS TLB usually have 32 or 64 of these entries. So in here we have 32 example. Sometimes it can have 64 entries, most of which are used by user processes as they run. So it is allocated as they run. However, a few other are reserved for the OS. A word register can be set by the OS to tell the hardware how many slots of the TLB to reserve for the OS. So some of these bits are actually used for or allocated for the OS to tell how many slots of the TLB are reserved for the OS. The OS use these reserve mappings for code and data that it wants to access during critical times when a TLB miss would be problematic, like in the TLB miss handler. So this kind of like in the page table handler, some bits of this are used for a TLB miss handler. So just like in a page table, TLB also has an OS bit for a TLB miss handler because the MIPS TLB is software managed. There needs to be instructions to update the TLB. So because it is software managed or the OS managed, there should be a code or instruction to update the TLB. So we need to do that in an if-else update that software we have earlier. The MIPS provide for such instructions. TLBP, which probes the TLB to see if a particular translation is there. So it provides this syntax that contact the hardware, which probes the TLB to see if a particular translation is there. Syntax TLBR, which reads the contents of a TLB entry into registers. TLBWI, which replaces a specific TLB entry. And TLBWR, which replaces a random TLB entry. The OS uses these instructions to manage the TLB's contents, whether it's virtual, from VPN to physical frame. It is of course critical that these instructions are privileged. So it is designed in the its if-else statement to be only activated in privilege. Imagine what a user process could do if it could modify the contents of the TLB hint just about anything, including take over the machine, run its own malicious OS. We have seen how hardware help us make address translation faster by providing a small dedicated chip TLB as address translation cache. Most memory references will hopefully be handled without having to access the page table in main memory. Thus, in the common case, the performance of the program will be almost as if memory isn't being virtualized at all. An excellent achievement for an operating system and certainly essential to the use of paging in modern systems. However, TLBs do not make world rosy for every program that exists. In particular, if the number of pages a program accesses in a short period of time exceeds the number of pages that fit into the TLB, the program will generate a large number of TLB misses, and thus, so if the TLB available is less than the number of needed by the program, you have a lot of TLB misses, and thus quite a run bit more slowly. We refer to this phenomenon as exceeding the TLB coverage, and it can be quite problem for certain programs, such as a database, any large program. One solution, as we'll discuss in the next chapter, is to include support for large page sizes by mapping key data structures into regions of the program's address space that are mapped by larger pages. So one of the solutions here is to provide a larger pages or for that particular large programs. The effective coverage of the TLB can be increased. Support for large pages is often exploited by programs such as database management system, which have certain data structures that are both large and randomly accessed. So it's randomly access the database because sometimes you really use that. So therefore, you need to provide a different kind of memory or virtualization of memory for that, unlike the most frequently used program. On other TLB issue worth mentioning, TLB access can easily become a bottleneck in the CPU pipeline. In particular, with what is called physically indexed cache. So sometimes the TLB could have this bottleneck in CPU cache in the actual hardware. With such a cache, the address translation has to take place before the cache is accessed. So in this physically indexed cache, an address translation must be converted before you can access the cache, which can slow things down quite a bit. Because of this potential problem, people have looked into all sorts of clever ways to access caches with virtual addresses, thus avoiding the expensive step of translation in the case of a cache hit. Such a virtually indexed cache solves some performance problem but introduces new issues into hardware design as well. So it's an expensive step of translation in the case of cache hit. Because of that, virtually indexed cache solves some performance problems but introduces new issues into hardware design as well. So it introduces a new design or new hardware. It requires a new hardware setup. So paging smaller tables. We now tackle the second problem that paging introduces. Page tables are too big and thus consume too much memory. So another problem with page table is that they're too big and consume too much memory, like we discussed. So let's start out with the linear page table. As you might recall, linear page table gets pretty big. Assume again a 32 bits address space, 2 raised to 32 bytes with 4 kilobytes, 2 raised to 12 bytes. So we will solve this problem moving forward, and also we will tackle a large process like database management on how we can actually allocate space for that in the next video.